The very last test we're going to look at is a single factor Anova test. The notation over here, we have K different groups, the number of populations or treatments being compared. We would have, our labeling, we would have all these different groups. We have the population mean, which is mu1, mu2, all the way through mu k. We have the variance, which is sigma 1 squared, sigma 2 squared, all the way through sigma k squared. Our sample sizes are n sub 1, n sub 2, and so on. Our sample mean x1 bar, x2 bar, and so on. Sample variances are our s1 squared, etc. So we have a total of capital N observations. And over here, we have the overall mean, which is an X double bar. Our assumption are that each of the K population or treatment response distributions are normally distributed. And also we need to have the same standard deviation. So the K normal distributions all have equal standard deviation. Now these are the population standard deviations. We only have our sample data to go by, so we're going to look at our sample data and determine whether it's possible that they come from populations with equal standard deviations. The observation in each sample are independent, and the samples are selected independently from one another, or otherwise random assignment has been made to treatment groups. So just like we did with the chi-square test of homogeneity, same kind of ideas. So we're going to set up our null hypothesis. Our null hypothesis is that our means are, and these are our population means, are all equal. So the true means are the same for all population or treatment. And the alternative is at least one mean is not the same. So this allows us to compare more than two groups or more than two means. If we just had two means, we would do a two-sample t-test. A two-sample t-test also allows us to test for certain direction, whether one mean is greater or less or not equal to the other one. Where over here, we're simply checking, are they all the same, or is at least one of these not the same? So our first example we'll look at is different midsize cars. So we look at the mean gas mileage from midsize cars, SUVs, and pickups. And our null hypothesis is that the mean gas mileage is the same or are the same for all of these groups. The alternative is not all the means are equal. And then we calculate our test statistic. So again, the test statistic from Anova comes from an F distribution, where F is looking at the variation among the sample means. That's looking at really the variation between the different groups, and it's dividing it by the variation among individuals in each sample. So that's the variation within each group. We do have this complicated calculation, which generally we don't do this by hand. I'm going to show you guys some example with technology instead. But we do have the means given for these different groups, and so we're going to plug them in and look at the calculation over here. There are two different degrees of freedom. The first one is n minus, this is supposed to be a k, and the second one is k minus 1. So the degrees for between is k minus 1, and the degrees of freedom for within the groups is capital N minus K. So to calculate the test statistic, again, we plug in over here, we have our sample sizes, we have our X bars, so our means given. And so we calculate our test statistic, which is 40.053. So our 2 degrees of freedom from above was 3 minus 1, which is 2, and 62 minus 3, which is 59. Next, we're going to calculate the p-value based on our test statistic. So here we go. We're going to go second vars in order to go to the distributions. We are going to the FCDF over here. Our lower value was 40.053. Our upper value is E99. Our degrees of freedom in the numerator was 2. The degrees of freedom in the denominator was 59. And then to find our p-value, which is 1.027 times 10 to the negative 11th. So as a decimal number, we would have 10 zeros before the 1. So it's approximately 0. So over here, our p-value is 0, or approximately 0. And therefore, we're going to reject the null, which states at least one of the means is different.